In this short video, I just wanted to introduce the circuit elements for the electronics merit badge. There's not going to be any worksheet or anything associated with it. It's just sort of when you show up, you have some idea about what the different elements that go into in a circuit. And the first one is a resistor. So resistors are circuit elements, and they perform a wide variety of jobs, but what they do is limit the flow of electricity in a circuit. So the symbol of a resistor is sort of this up-down pattern that you see right there. So this is the symbol. And then on a circuit board, this is what a resistor would actually look like. And the important thing is that resistors follow Ohm's law. And this is Ohm's law down here, that basically the voltage across the resistor, and so if you took what's called a multimeter, and it has a little switch here, and you can measure voltage, current, and resistance, and it has some wires, and if you measure, say, from here to here, the voltage across that resistor is equal to the current flowing through it, I, times the resistance of the resistor. And the resistance you find from that previous video depends on the color band. It could be like, say, 100 ohm or 1,000 ohm resistor. And when you buy a resistor, it has a specific resistance, like I said, and the value of the resistance is the units is ohm, so it's always 100 ohm, 1,000 ohm. And the higher resistance, the more the resistor will prevent the flow of electricity. So here I've drawn out two circuits, and so we could have like a 9-volt battery right here connected to a resistor, and we want to know what the current running through the resistor is. And if we use Ohm's law, we say 9 volts times equals the current times the resistance. And for this particular example, I'm using a 1,000 ohm resistor, and we just solve for I, and it comes out to 0.009 amps. That's the unit of current, is amperes, or in scientific notation, you would just call this 9 milliamps. And if we used a bigger resistor, say 100,000 ohms, or we'd call this 100 kilo ohms, in the same type of circuit where we want to solve for the current, then we would just plug in the 9 volts from the battery, the 100,000 ohm resistor, and solve for I, and then we'd get 0.00009 amps flowing through the circuit, or this would be, we would call this 90 microamps. So that's resistors. Their primary job is to limit the flow of electricity or current inside of a circuit. Another useful application of resistors is to create a new voltage, and we call this type of circuit a voltage divider. So here I have, say, some battery or power supply that's giving you an input voltage, and it's going to two resistors, and we're taking the output of the circuit across resistor 2, and that voltage output will be different than the voltage input. So here is the formula. The voltage output is equal to resistor 2 divided by the sum of the resistances of resistor 1 and 2 times the input voltage, which was this guy here. And you could also use algebra to solve for different ones. If you knew, say, the input and output voltages, and you had one resistor fixed, then you could solve for the other resistor. But here's the example. Let's say you have a 9-volt battery, so this is 9 volts. For your input voltage, and R1 is equal to 1,000 ohms, and R2 is equal to 1250 ohms. What is this output voltage going to be? What is that? And so you just use this formula right here. And you say, you plug in what you know. So R2 is 1250 ohms, R1 plus R2 times the input voltage. And so now our output, instead of being the 9 volts from the battery, it's now 5 volts. Okay, so let's go on to the next circuit element. It is called a diode. And again, diodes do a lot of different things, but what they mostly do is make the electricity flow in one direction. And there are a lot of different types of diodes, but we'll focus on just two. Just the plain old diode and the light emitting diode. So this is the plain diode, and this is the circuit symbol. If you were going to draw out a circuit, this is the symbol that you would use to represent there's a diode in there. And the arrow shows the direction of flow of current, and you could think of this vertical line here as like a wall if it was going to go this way. So current can't go in this direction. It can only go in that direction. Remember I said the diode does a lot of things, but what it does is it only allows, I shouldn't say it makes, it only allows electricity to flow in one direction. And then we have the light emitting diode. It still has the same diode symbol, but it emits light. And you can see here is what a light emitting diode would look like. LED. And an LED will only allow the electricity to flow in one direction, but it also makes light. And if you look at a real diode, here's a real diode right here, instead of just its circuit symbol, this little band right here is basically this circuit symbol right here. So the direction of flow for the electricity is this way. And then for an LED, the direction of flow of electricity is, you can see on this picture here that for the actual LED, there's one leg that's kind of longer here, and that's going to be hooked to the higher voltage, and this one's going to go to the lower voltage. So the direction of flow of electricity is going to be into here and out here. So on this page, I say a diode needs a certain voltage to activate. At voltages below activation voltage, the diode will not conduct electricity, and the circuit will have no flowing current. And so for a red light emitting diode, it needs 2 volts to turn on. So here I've shown a simple circuit. Again, we could have like a 9-volt battery right here, and say a red light emitting diode. And the LED would light up for a while, but would burn out in this configuration because the LED does not limit current and will overheat and destroy itself. So we could hook this up, and it may run and it may turn on and you see some red light coming out, but after a while it's going to stop because it's just going to get too hot. So we needed 2 volts to turn it on, and that's supplied by the battery, but the LED doesn't limit its current. It'll just let as much as it wants flow through. And so what you need to do usually for an LED circuit is put in series, one after the other, a resistor. Remember, resistors limit the current in a circuit with your LED. And that way you won't burn up your LED. So right here I've said when you buy an LED, it will state the necessary voltages to turn it on, like 2 volts here for the red LED, and the maximum current that it can handle. And so most of these ones that I show on this previous page, these types of diodes, light emitting diodes I should say, it's around 0.02 amps or 20 milliamps is the maximum current that can go through it. Otherwise they'll just burn themselves up. And if you wanted to figure out, say, what is the value of the resistance that you needed to put in series, you could use this procedure to solve for that resistance. But you have to use another little law that's used in electricity and electronics, and that's called Kirchhoff's voltage law, which basically says the sum of all voltages around a loop is 0. And so if we go around this loop and there's a current flowing through it, it says the sum of all these voltages have to be 0. So we have the 9-volt battery. It has a voltage. When current's flowing through it, a resistor, it has a voltage. Then we have the 2 volts that are needed to turn on the resistor, and all that's equal to 0. And since we're going in this loop, as I've drawn it, we're going into the minus side of the battery, right? Minus 9 plus, this is Ohm's law here. Remember, V equals IR is Ohm's law. Plus 2 equals 0. And then we plug in minus 9, that's the battery, plus 0.02 times R. And you say, where did I get that 0.02? Well, I'm just putting in the limit of 0.02 for the LED. You don't want to go any higher than that. Times R plus 2 equals 0. And then we just use some algebra to solve for R. So if we put in a 350 ohm resistor, we'll say R equals 350 ohms, in this circuit, then the current will be limited to 0.02 amps, okay? And you won't burn up your LED. You could use a bigger one just to be on the safe side. So if I was going to build this, I might use like a 4 or 500 ohm resistor, but you need to have at least a 350, otherwise you're going to have too much current flowing through it and it'll burn up your diode. Okay, the next circuit element are capacitors. And again, they do a lot of different things, but what they do is store energy in a circuit. So here is the circuit diagram symbol for a capacitor. That's the symbol. And on a circuit, this is what capacitors would look like. These little round cylinders or ceramic discs, or these discs here. But again, there's just thousands of different sizes and shapes of capacitors. But on a circuit, they're mostly going to look like what I see in this picture right here. And when you buy a capacitor, it has a specific capacitance. which is basically how much energy it can store. Like I say right here, the higher the capacitance, the more energy the capacitor can store. And that capacitance is given in a unit called farads, or the symbol F. So here I'm showing just a little demonstration of capacitor circuit. So here we have a 9-volt battery again, and we've hooked it up to a 10 millifarad capacitor. And this part here is not hooked up to anything, so you could just pretend it doesn't exist for the moment. It's just a resistor in series with a LED, and the LED is not on because it's not hooked up. So once we open this S1 and S2 are switches, and once they move, then we get this situation. So the switches moved, S1, and S2 moved. Now the battery is no longer in the circuit, and the capacitor will just discharge its energy through this circuit over here and light up the LED. You can see here the two arrows are kind of lit up. And so you can see here that the capacitor was charged by the battery, and then when we turn the switches, then that charge flows out through the circuit and lights up the LEDs. Capacitors don't hold a lot of energy, for the small ones at least, and so it'll just light up for a little while. But they are used for, you can use the same capacitor for decades, and whereas a battery only lasts for a short amount of time. And here's some other common applications. They can used as filters to remove some electrical signal. They're also very common in power supplies. You know, when you have a laptop and there's this brick outside that you plug into the wall, it'll have some, it has to take the AC voltage coming from the wall and make it into DC voltage for your computer. And so that, to make it very smooth DC voltage, it'll have capacitors in it. And then if you have like a radio or antenna or something like that, those are used to actually tune it to the correct channel or frequency. One other thing just to note is capacitors block DC electricity. And remember in that other electricity video, I had like a graph of time and voltage. For DC current or signals, it's always like the same. And then for AC, if we were to look at time, so time is increasing, and we have voltage, then you have a sine wave. And so DC voltage will not flow through a capacitor. And so if I was to hook this all up, 9-volt battery was a capacitor plus a resistor, the LED would not light. Or it might, well, actually it wouldn't light at all. It wouldn't light at all because only AC current can flow through a capacitor, not DC. Okay, so the next thing is transistors are a circuit element. And again, they do a lot of different things, but their two common applications are amplification, that means making an electrical signal bigger, and switching, turning something on or off, like a light switch. There are many different types of transistors, okay? But we're going to focus on one specific type of transistor. It's called the bipolar junction transistor, but you can just call it BJT for short. That's what everybody calls it. So a transistor is used for amplifying a signal, making it bigger, and switching, turning something on or off. Okay, and there are a lot of different types of transistors. The most common one is called BJT. Okay, and here is the symbol for BJT, if you were to draw it in a circle. And there's two types of BJTs. There's called the NPN BJT and the PNP BJT. Okay, and here's the symbol. And the difference is, if you look right here, this arrow is pointing away, and this one is pointing towards. Okay. And in real life, if you looked at a circuit board, this is what a transistor would look like, right here. And it's a 3-terminal device. You know, like a resistor, it just has the input terminal, the resistor, and the output. And like a capacitor, again, or an LED, those are all 2-terminal devices, okay? And one is called the base, so we call it B, base. And this is called the collector. And this is called the emitter. So the same thing. The difference between the two is just how you hook up the power supply. So we're not going to focus on this guy. But if anyone ever asks you, what is that symbol on the merit badge? This is the electronics merit badge. And you can see right here, it's actually a PNP BJT. So a PNP bipolar junction transistor is actually the symbol that's on the electronics merit badge. And again, to go back to it, the job of a transistor is usually amplification or switching. And I'm just going to focus on amplification, just to make it simpler. And here I've drawn out in a circuit simulation software. Here's a, again, a NPN BJT, bipolar junction transistor. And if I hook it up into a circuit, this is the base. Remember, this is the emitter, and this is the collector. And generally what happens is you put in a weak signal here, weak signal, and weak meaning it's very low voltage. And you get, at here, you take the output of the circuit from here to here, V output. You get a big signal. Okay, and current will flow, a little bit of current will flow in here, and a lot of current will flow down from the collector to the emitter. And so in my circuit simulation, you can see I'm putting in 43.1 microamps. So that's 0.1234 amps. So a very tiny number. And then we're getting out 0.00903 amps. So much bigger. So that's the amplification that we're talking about. And if I change this resistor here, this one right here, and make it twice as big, I went from 100,000 ohms to 200,000 ohms. The current went down in half, so 21 microamps, and the output went down. So by controlling what happens at the input of the base, we can get amplification at the output of the base. And here I've taken that exact same circuit, and what I've done is I've put in a weak signal. I've hooked it up to a weak signal in the circuit simulation software. And so I'm just putting in if you were to use a meter and look at this time, you would have a little signal here. So the 0.005 volts. So 5 millivolts signal. And if you hooked up a meter here from this point to this point and looked at the signal coming out over time, it would be 100 times bigger. So this one was 5 millivolts, and this is 500 millivolts on the output of the circuit. And so our signal has become much larger. And you could use this, say, as I just put in the circuit simulation a voltage source, but this could have been a microphone. And then the output could be, say, a speaker. And so the signal was amplified. So there we have it. The common circuit elements for the electronics merit badge, and the most difficult, of course, is the transistor, which can be confusing if you've never seen it before. I'm sure that it's very confusing if you've never seen it before. But the main thing I just want you to know when you look at it, see a transistor, someone says a transistor, I know it's used for making signals bigger, and it's used for switching. And if anybody asks you what's the symbol on the merit badge, you can say, I know that that's a transistor on the merit badge.